Fine. Okay, so let me wait for a few minutes, then I will start. Okay, so let me start today's lecture. Uh, so in the last lecture, we have primarily, last two lecture at least, we are primarily solving the Landau levels. And we have, so the last lecture was specifically solving Landau levels for graphene in the symmetric gauge, right? And what I see or we have shown is that once you apply sufficiently high magnetic field, then continuous spectrum of graphene, or for that matter, any material, two-dimensional electron gas is another example. So there is a development of discrete energy levels, which we call Landau levels, right? And we studied the various properties of this Landau level wave function in the symmetric gauge, how it varies with the radius, specifically the wave functions radius. where at which the wave functions peaks was something associated with the angular momentum of those wave functions and so on. Okay, so all of those uh, concepts are going to be useful in studying quantum Hall effect. Okay, so I'll try to give a bit different perspective than what is, or at least not really different perspective, but I'll cover some of the things which are already there in the lectures, and then some of the things which may not be there in the lecture in a great detail. Okay, so it'll be brief, but my plan is to capture the essence of quantum Hall effect as uh, simply as possible. So, so before understanding quantum Hall effect, what we know from our basic solid state physics is that if we plot the resistivity, right, versus the magnetic field as a function of magnetic field, you what you see is that this is my rho xx curve, okay, uh, and then which is independent of B, okay, because rho xx is something related to the sigma xx Drude. So this is the Drude conductivity which is independent of magnetic field. Okay, so this is the Drude picture of conductivity in presence of magnetic field, which is sort of the first chapter of any solid state book, let's say. And there is transverse resistivity, which appears only when you apply some finite magnetic field, which was like something like this, rho xy, and rho xy was uh, B by NE, right? Let's say if we are considering for electrons only, then this is B by Ne. B is the applied magnetic field, N is the number density or the electron carrier density in the sample, and E is just the electronic charge. So it linearly varies with the magnetic field, and once you put the magnetic field to be zero, this is the resistivity is also zero, right? Unlike the rho xx, which has a constant value all over, I mean, you apply any magnetic field, it is essentially remains constant. So this is what we also see here. So this is a data so this plot is a data of quantum Hall effect for two-dimensional electron gas. Uh, so what you see is that so this left hand side or left axis is the rho xx and then right y axis is the rho xy, right? So this is the red curve is rho x6. So what you see here is that this is almost constant at low magnetic field, right? So this magnetic field is in Tesla. So if you have a very low magnetic field up to maybe 1 Tesla, it is almost constant, as you can see. And then it oscillates, right? And then the rho xy, as it should be from this classical Drude picture, it is linear in the magnetic field, just like this one. And then as you increase the magnetic field, again from beyond 1 Tesla, let's say, so there is a development of plateaus, right? It's instead of going linearly increasing, it goes something like this. Then there is a plateau. So there is a window of magnetic field. So from this to this, let's say you are increasing the magnetic field, there is no increase in the resistivity, transverse resistivity, and then at some particular magnetic field it just crosses, or I mean there is a jump in the resistivity, and then there is again a plateau where up to some magnetic field again it doesn't change, and then this keep on increasing, right? As you increase the magnetic field value, these are pretty high magnetic field value, okay, 10 Tesla, 12 Tesla is sort of uh, very high magnetic field value, and there is a more well resolved plateau that you can see, and yeah, so that's sort of the behavior of the transverse resistivity or the Hall resistivity in simple words. And something very interesting and very counterintuitive that happens with the rho xx longitudinal resistivity, right? So what really happens is that at very low magnetic field it is constant as predicted by Drude model, but then there is some oscillation which can be understood from Subnikov-Diaz oscillation, again something that we have not covered, but there is oscillation, Subnikov-Diaz oscillation, but then the more important point for this rho xx is that every time the rho xy changes to the next plateau, there is a jump in the, or there is a finite rho xx, right? But then as long as you are in the within the plateau, within the range of the magnetic field where the rho xy is constant, the rho xx is zero, right? Again, there is a transition for rho xy, so there is another peak for rho xx, and this keep on increasing. I mean, keep on happening, right? So this was a puzzling puzzling behavior for us, that how do we explain the simultaneous behavior of rho xx and rho xy for this kind of once you apply very high magnetic field in two-dimensional electron gas, whether it can be free electron gas, two-dimensional free electron gas, which initially uh, so the first experimental observation was done in gallium arsenide quantum well. It's a 2D quantum well. But then later people observed in graphene and many other 2D materials as well. Okay. So this is what we call quantum Hall effect, because the rho xy, the resistivity or the transverse resistivity, or we can also call Hall resistivity, is quantized, right? And it is given by 1 by nu h by e square. And the nu can be 0, 1, 2, 3, and so on. Sorry, this should be 1, starting from 1, and so on. So these are integers, and then these resistivities are essentially quantized, right? Okay, so we'll understand a lot of caveats, a lot of I mean interesting points about it. But when this kind of quantum Hall can appear, right? If you talk in terms of energy scale, then quantum Hall effect appears when h bar omega b is the largest energy scale in the system. Okay, so largest energy scale. So there are quite a few energy scale in the system, in a solid state system. For example, one is your chemical potential, right? Typically of the order of EV or sometimes milli electron volt as well. Again, depends on the system. And then you have intrinsic KBT, which is temperature scale, right? Again, so these experiments are done at a very low temperature. So the temperature is of the order of, let's say, uh, so so the temperature of the order of few Kelvin at max. Okay. And rather, for graphene like samples, people usually experiment with the millikelvin level temperature also. So the corresponding energy scale for few Kelvin, which is given by KBT, is again will be some few MeV. Okay. So one way to look at this is the KBT for room temperature. Okay, which is of the order of 25 MeV. Okay, so if you talk about few Kelvin, and the room temperature means 300 Kelvin approximately. Okay, so these are just rough scales. So this is two important energy scale, and then there can be in realistic samples you will always have some disorder, some dirt in the material, right? You want to make the device as clean and as perfect as possible, but then practically there is always some level of disorder or impurity and so on, right? So what do we mean by disorder or impurity? Is just that you have a pristine sample, let's say graphene-like sample, and then there is some other particles in the graphene sample. In simple words, that's the disorder. So the disorder energy scale is also very low. Okay, is also smaller than h bar omega b, kVt, and so on. Okay, so the point I'm trying to make is that this kind of quantum Hall resistance is going to appear when h bar omega is the largest energy scale system in the system, right? Right. So h bar omega b will be larger than kBt. It will also be larger than mu, and then of course the disorder also. Okay, and also the mu is going to be greater than kBt. Otherwise, uh, I mean, the thermal noise or the thermal smearing will disappear, or because of thermal smearing, you will not see the well-defined plateaus. Okay. Okay. So simultaneously, what we have is something like this. We have rho xy to be quantized and rho xx to be zero at certain magnetic field values, right? And certain magnetic field window where rho xy is, rho xy has some plateau. Now, the important one interesting point is that the following. So, so let me write color. So what we have is that rho xx is zero. Okay. So when rho xx is zero, what we mean by that is that it's behaving like a perfect conductor, right? So there is no resistance in the longitudinal direction, so it's behaving almost like a perfect conductor. But then if you extract the sigma xx, which is the conductivity, corresponding conductivity, we have something like this relation plus rho xy square, and then sigma xy equal to minus rho xy by rho xx square plus rho xy square, right? So if rho xy equal to 0, so if your rho xy equal to 0, right? So you have no transverse conductivity. Transverse Hall resistivity is to be 0. Then what you have is that rho xx is 1 by sigma xx, which means that conductivity is inversely related to the resistivity, which is what we know. But then when you have rho xy not equal to 0, which is the case for quantized Hall conductor, Hall resistivity, then what we have is that, so whenever your rho xy is non-zero, right? So this is a non-zero rho xy, let's say this one. So then, but then at this plateau, your rho xx is 0, right? So rho xy is non-zero and then rho xx is 0. What this necessarily means is that sigma xx is also 0, right? This means that conductivity of the system, quantum Hall system, is 0. And when do we call conductivity of a system is 0? When it is an insulator, right? So perfect insulator means no, there is no conductance. Okay. Okay, so then if you combine these two facts, that rho xx is 0, which we call perfect conductor because there is no resistance or resistivity, and then sigma xx is 0, which we call perfect insulator, right? Which is to say that there is no conduction happening. So this is simultaneously this is happening, right? But this is a counterintuitive. So what is really going on? That in a system, I have the rho xx equal to 0 and sigma xx is also equal to 0. This particular surprise or the counterintuitiveness is something more to do with the way we say these things, meaning something more to do with the words than we just describe the underlying physics. Okay. So what is really the point is sigma xx equal to 0. This tells us that no current is flowing along the longitudinal direction. So you have I mean, four probe geometry, let's say. So you have a sample like this, maybe, and then you have a contact here, here. So this is a source, and this is a drain, and you apply some voltage, right? And so let's say current is flowing along this direction. So there is some current, and then there are other contacts, and you measure hall voltage from here. Okay, VH, hall voltage here. Okay, along the perpendicular direction to the current. Now sigma xx0 tells us that the no current is flowing along this direction. Okay, so there is no current along the longitudinal direction, although you have applied some voltage, but there is no current along the longitudinal direction. And so it's like an insulator. While the fact that rho xx is equal to 0 is telling that there is no dissipation of energy. So there is no resistance, so there is no dissipation of energy. Okay. Okay, so with this, let's move to, I mean, so, okay, so what this necessarily implies that you have, when you have rho xx equal to 0, and then this is equal to sigma xx, but then rho xy is not equal to 0, you have a dissipation less Hall current, right? So there is no dissipating heat and so on in the quantum Hall system. Okay, so with this, let me move to the how do we explain the quantum Hall effect, quantization, and other aspects of it. Let's say, okay, so yeah, so when we studied the Landau levels, what we have done is that we have taken an Hamiltonian and then we quantize that Hamiltonian to get a bulk Landau levels, right? So initially, let's say for graphene-like system, you had a band dispersion like this. These are sort of low energy band dispersion, and then in presence of magnetic field, you had, I mean, the zeroth Landau level, and then there is a first Landau level, both side, and then second Landau level. So these are the quantized energy levels, right? And so on, right? So these are quantized levels. But what we have missed in this Landau level, conventional Landau level physics, is that we have missed, or we have not considered, two things. One, disorder, and second one is age. Because so any sample in reality have some physical dimension, right? What we have considered is that it's a periodic Hamiltonian, and so there is no concept of age and surface. So so everything is periodic, right? But then in a physical sample, you will have some age, and as well as in practical samples, you will always have some kind of dirt or impurity present in the system. It's so the practically you will never have a perfect sample. Okay. And these two elements, the reason I am including I mean discussing these, that these two are equally important in explaining the quantization of the resistance, Hall resistance, and then how why these the longitudinal resistance becomes zero, and then during the transition from one plateau to another plateau, it develops some value, right? Some peak. Okay, so let's first look at the disorder case. Suppose we have a Hamiltonian like this, sum over ij, okay, minus t. This is a tight binding Hamiltonian, and then ci dagger plus Hermitian conjugate. And then we add the disorder at some places. I mean, each Ci dagger and Ci. So I denotes the lattice sites. Okay. So this is my periodic part of the Hamiltonian. Uh, So this is my periodic part of the Hamiltonian, and this term represents the disorder. Okay, Vi is the disorder strength. So I have, let's say, if we think about the graphene itself, then let's say, so these at each corner there is some atom, right? And the hopping between these atoms are represented by minus t, and it goes on, let's say, right? And then randomly there are some disorders. So let's say at some potential. So this is ith position, and then so there is some disorder sitting here, and then there is some. Let's say this is some I plus three, let's say, or whatever it is. So there is some disorder, and so this is randomly distributed. Okay. And what this breaks is that because of this disorder, the translational symmetry or the perfect periodicity in the system is broken, right? So because of this Vi, so when Vi not equal to 0, that means translational symmetry is broken. Okay. Now, in for a periodic sample, we can kind of do the Fourier transform and go to the K space. So we have a Hamiltonian in the real space, let's say, and then by doing Fourier transform, we can go in the K space and we solve this Hamiltonian, basically diagonalize the Hamiltonian to get what will be the energy in terms of momentum, and then what will be the wave function in terms of momentum, right? But because of that translational symmetry is broken in presence of disorder, we cannot do this. Fourier transform cannot be done because of the breaking in the periodicity. So, so, but what we can do is that we can think about the what happens to the density of states, right? So you have a, let's say so you have, let's say, Landau levels, something like this. Or if you, even if you don't think about the Landau levels, you can simply think, so there are some bands, let's say, uh, so there are some bands, let's say, so these are zero field case, so b equal to 0, let's say, and you have some density of states. So along this direction you have density of state. Okay. So within the band you will have some DOS, right? So you will have some DOS, let's say, along this, I mean, up to this energy, and then up to this energy, you will have some DOS, and there is a gap in between, right? So let me draw that thing. Yeah, so draw DOS here. Now, so this is the in absence of disorder, let's say, right? And what disorder does is that it broadens these energy levels, or the density of state. So initially, your let's say the band ends here, then your density of states is also exactly at that point. So your bands is up to this point, then the density of states goes to 0. So this is a 0, and there is some value here at least. Okay, so your this band is starting here. So from this point you have some density of state, and this band is ending here. So you'll have density of state up to this point. Okay. So this is the no disorder case. When you have no disorder. Now when you have some disorder in the system, what happens is that these density of states gets broadened. So something like this. Okay. So the green curve says no disorder, and then blue, there is some disorder. Okay. Okay. And this particular part, so 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 So I'm highlighting by yellow color, let's say. Okay. So these are called mobility edge. So this black colored uh, are the mobility edge. Okay, and these are delocalized states. Uh, so these parts are delocalized states, and beyond this, so it's becoming too crowded. So let me use a different color. The localized state. Okay. So what really happens is that you had a density of states up to this when you had no disorder, and then the in presence of disorder, the density of states get broadened because there are other states that is happening or that is there because there are some impurities and so on. So these particular the density of states are contributed by the disorder. Okay, and the earlier density of states in absence of disorder are give rise to delocalized state. Okay, so these are consistent with the block theory. So the electrons sitting within this density of states are essentially delocalized, so they can move the moment you apply some external perturbation and so on. But then, although the in presence of disorder, you have extended density of states in this region, right? The pink region, but then they are localized states. Okay, so they are not going to I mean, so the electrons with this kind of the density of states are not really mobile, so they will sit at the same point basically. And the boundary between this localized and delocalized state is what we call mobility edge. Okay, so this will be important in understanding the stable plateaus in the system, and as well as why there is the development of longitudinal resistance. So if we think about more clearly and more easily, so suppose you have a periodic system, or I mean so these are some atoms in the lattice 1D. I'm drawing it 1D, but then the idea can be extended to other dimension. So initially you had delocalized state. What do we mean by delocalized is that the electronic wave function has some kind of this, right? So anywhere you have some, I mean, probability to find the electrons, right? So essentially the electrons are almost free. But in a periodic solid state system, this is essentially given by the block wave function, which are not really exactly free wave function, block wave function, which is not really purely free because psi is of the form of u and k and then e to the power I k dot r, right? So e to the power I k dot r is the free part, free electronic part, or yeah, free particle wave function. But this is dressed with some UNK, and UNK has the periodicity. So UNK at any position, real space position of a crystal lattice, is same as UNK crystal lattice plus the Bravais lattice vector. So R is the Bravais lattice vector. Okay. Okay, but so this is in absence of disorder, but in presence of disorder, what happens is that the states get localized. So initially it was like this, and then you will see something like this. So the states is localized along, I mean, maybe here also. So earlier you had a extended state. You can the probability of finding electron can be anywhere. Electrons were almost essentially behaving like free. But then in presence of disorder, what really happens is that electrons are localized, right? So if you think about the probability, then the probability of finding electrons at these sites are very high. But then at other places, it is essentially almost zero or very small. Okay, so this means that the electrons are localized around these sites, and then it is I mean, unlike the delocalized state like this earlier, right? Okay, and this localization happens actually because of Anderson localization. So there is this is a famous phenomena in condensed matter system, and there are a lot of studies earlier. So this localization. And according to theory of Anderson localization, so there are three kind of system we have, right? Generally, so 1D system, 1D system plus disorder. So imagine you have a 1D periodic system, and then you put some disorder in the system. It says that it will always localize in thermodynamic limit. So what this necessarily means is that you have a only chain of atoms, and then you put some disorder on it. Your earlier the electrons are delocalized, and then electrons can, let's say, carry electricity, or I mean, electrons can carry current. You have essentially free electrons, or rather block electrons. But once you put disorder, the system will start behaving like an insulator, because the electrons are now localized. They do not want to move to other places. Uh, so that means the you will not have any current once you apply some voltage, right? Uh, then if you have 2D system, so these are all B equal to zero case, and then we will connect to the B not equal to Landau level case. Okay, so 2D system plus disorder. Again, you will see the same. And by the way, 2D system plus disorder was studied by Anderson. So this is a scientist name, and our one famous Indian scientist called TV Ramakrishnan. Okay, the full form I do not know the full form. TV, not forgot, but so he's a professor at IISc. So these guys have a series of very famous papers at the uh, 1980s and so on, even 1990s also few papers. Okay, so this case is also the same as 1D case. So it will have always localized. So when we say always localized means that no matter how small disorder is present, I mean, you have a pristine system and there is a very small amount of disorder in the present. So maybe one atom or two atom, which is, let's say, displaced, or there is some dirt or impurity present in the system within a clean system. It doesn't matter how small it is, very small amount of disorder will also make the system localized, meaning earlier you, let's say, started with a metal, it will behave like an insulator in presence of disorder. So always localized in thermodynamic limit. And then there is a 3D system. plus disorder. So this is something different. This says that there needs to be a critical disorder strength. Okay, so localized beyond a, okay, okay. And these theories or this understanding is that sorry. So all the above disorder theory, let's say, theory are for free fermionic system. When there is no magnetic field is zero. Also, the electron-electron interaction we also do not consider. Okay, okay, okay. So now, what we have at our hand is that 2D system. Okay, so our interest of study for quantum Hall system is that we have a 2D electronic system, right? Plus we apply some magnetic field, plus we have disorder. Okay, so this is the complete. So these are the three ingredients that we need to understand the quantum Hall physics. Okay, at least the integer quantum Hall physics. Now, for the fractional quantum Hall, along with this two-dimensional electron gas plus magnetic field plus disorder, you need another element which is called electron-electron interaction or correlation. Okay, but we are in the integer quantum Hall regime. Okay, so now. So we have, let's say, so if we think about graphene, let's say now, right? So graphene earlier, we had the, I mean, so if we draw the Landau levels, let's say you had a Landau level at n equal to 0, so n equal to 0, and then somewhere here n equal to 1, and then n equal to 2. Okay, so these are typically called n equal to -1, and then -2, and so on. And so when they are perfectly perfect, so in absence of disorder, let's say, so these are the just line, right? These are just lines. So if you plot the density of states, they are going to peak at exactly at the energy. So along this axis you have energy, and along this axis you have density of state, right? So the density of states essentially means that how many states are there in that energy, right? So you have energy at exactly this energy, so you have a perfectly, I mean, it's like a Dirac delta potential, perfect Dirac delta potential, where you have a some density of state here, and then once you if you think about this n equal to 1, you have some density of states, n equal to 0, you have density of states, n equal to 1, again you have density of states, and then n equal to -2, again you have some density of states, right? So the point is exactly at the energy where the energy Landau levels lies, you have some density of states, and these are not broadened density of states, rather infinitely sharp Dirac delta type of potential. Now, in presence of disorder, as I told you earlier, these gets broadened, so somewhat looks like this. Okay, for the case of graphene. And then the concept of mobility age and then localized states and so on are actually here also valid. Okay. So the important point to remember is that uh, so there are delocalized state exactly at the energy, right? En can be 0, 1, -1, and so on. And then except at En, all other state are localized, right? Okay. Okay. Now what really happens when the electrons, I mean, you vary the magnetic field. So when you vary the magnetic field, let's say you have this kind of density of states, this kind of energy levels, and you have a Fermi level somewhere here. Okay. So let me draw with a different. So you have somewhere Fermi level, right? Fermi energy. Now, as we increase the magnetic field, so when you increase the magnetic field, two things happens. One, the energies of these n equal to 0, n equal to 1, and so on, these energies also gets increased, okay? Because epsilon n, so epsilon n for graphene is something like this, root b, and then there are some factors, so maybe h bar vf square and so on. So as you increase the magnetic field, if you increase the magnetic field, then epsilon n for each Landau levels, the energy is also going to increase. That is number one. And as I told you earlier in the earlier class, that epsilon n minus epsilon, sorry, epsilon n plus 1 minus epsilon n, which is the gap, energy gap between the two consecutive Landau levels, this also increases. Okay. So this also increases as you increase the magnetic field. And so as you increase this, so essentially you start with, let's say, at some point here, and then you are increasing the magnetic field so that the energy also increases, and at some point this particular Landau level goes here, right? The crosses the of the Fermi energy. The moment you have so this particular Landau level or the zeroth Landau level somewhere here, right? That means at this exact point you have some states to conduct. What is happening? So whenever this Landau level crosses this Fermi energy, right? So you have some delocalized state exactly at these points, as I told you earlier. And these delocalized states, essentially meaning electrons are effectively behaving as free electrons, and you applied electric field and magnetic field, and because of this, the electrons can conduct the electricity. So every time a Landau level crosses this particular Fermi energy, you your electrons gets a window where the electrons are essentially delocalized and they can conduct electricity. So there is a finite rho xx. Okay, rho xx is not equal to 0 whenever uh, Landau levels crosses the Fermi energy. Okay, that means, so this means this explains the peak in row xx. Okay, so if I go to the earlier picture, so you had peaks there, right? So these peaks are appearing whenever your the Landau levels are crossing the Fermi energy. Okay, so every time they are exactly so. So let's say if I have a Landau level somewhere here and the Fermi energy is also here, so your density of states are like this. So there is a mobility edge, and because of this mobility edge, so these are the, the electrons get mobile and then they conduct electricity in the longitudinal direction as well. So this is what explains the peaks uh, in the resistivity, longitudinal resistivity, this part. Now, why this is zero, right? Now, to understand this, let's say what I do. So this picture is going to be very useful. So I am showing you the magnified picture. Okay. So imagine you have this. So you have a Landau level here, and so essentially what we have is that so this kind of density of states, and you have another Landau level here. So okay, so this is the exact Landau level energy, and this is the delocalized state, and somewhere here you have a Fermi energy. Okay, now suppose you increase the magnetic field, right? So these are localized state. Let me write that. So these are localized state. So, so whenever Fermi energy is here or here, or the Landau levels, so you can think in both the terms. Either you move the Fermi energy, which you can do in experiment by changing the carrier density, right, which is readily available in for 2D materials, or you change the magnetic field. Okay, so in both the cases, the similar situation happens. So when you change the magnetic field, what happens is that Fermi level gets fixed. Fermi level is something determined by the amount of electrons or amount the charge carriers you have in the system. So it is fixed. But then Landau levels in energies are getting increased, so they cross one by one. So there are other Landau levels here and below, so they get more and more energized, and then they cross one by one. Okay. On the other hand, if you fix the magnetic field, you change the carrier density. What this essentially means is that you are changing the carrier density. So essentially, you are changing the Fermi level. So initially you started with here, let's say, and you increase more carrier density. So Fermi level goes here, here, and here, so on. In both the scenarios, whenever your Fermi energy lies somewhere here, you have a delocalized states which conducts electricity, but then, this is what gives rise to the finite rho xx. But then, whenever Fermi level energy lies anywhere in between, so between these two green lines, let's say, so you have this localized states, which do not. That means that electrons are now localized and they are not mobile, so they do not conduct electricity. What this necessarily means is that rho xx is going to be zero now. Okay, so when Fermi energy or EF lies between two localized or delocalized state, or we can also say Fermi energy lies in the uh, within two consecutive mobility edge. So here will be one mobility edge. Sorry. So here is one mobility. What is really happening? So this is one mobility edge, let's say. Okay. And there is another mobility edge here. So mobility edge essentially distinguishes between localized and delocalized states. So the delocalized states are this. Okay. Okay. So when EAF lies between two delocalized states, or in the mobility edge, or in the or within the mobility edge, consecutive Landau levels. You have rho xx equal to 0. The physically what happens is that electrons are immobile. So no longitudinal current. This explains that why rho xx is 0 at certain magnetic field values. So what we are able to explain uh, by considering the two-dimensional electric field, two-dimensional electron gas plus magnetic field plus disorder is that you understand now that there is uh, the development of some amount of rho xx whenever the electrons are in the delocalized states, and in between the electrons the system becomes insulating, so there is no longitudinal resistivity. Okay, so this part is sort of explained with the two-dimensional electron gas magnetic field plus disorder. Okay, now what we still do not understand is that why there are some plateaus and why these plateaus are very robust, right? So what is really happening for this the Hall resistance? So to understand that, we need to introduce another concept, which is the edge physics. Okay. So earlier we had this 2D uh, 2D electron gas magnetic field disorder. Now we'll introduce on top of this we'll introduce uh, edge physics. So let me write down that explain the behavior rho xx in quantum Hall. Now the question that we are trying to address now is that uh, plateaus of Rxy. Okay, so this is our now target to understand, and for this we need to introduce another concept, which is the edge physics. Okay, okay, so I think this is a good place to stop. I mean, before proceeding, if you have any question, you can ask, or else we'll move. Okay, so let me move to the next part. I mean, the edge physics. Okay, to understand the role of age, or is there any role of age, uh, uh, we actually need to relook at the wave functions of the Landau level that we have discussed in the last class. And this is our big question, that what explains the plateaus in rho xy, right? So in the last class, what we have seen is that you have a, let's say, square shaped or rectangular shaped, I mean, sample. and we solved the Landau level for graphene in a symmetric gauge where we have seen that the wave function peaks somewhere here. I mean around the center, and as we increase the m was our uh, okay. Is there any question? I really have no idea about how the exam will be actually. Okay, so we are just so we do not set the questions as well as the assignments are also directly sort of under control of the instructor. But as far as I know, these advanced courses actually have pen and paper mode. And then there can be some lengthy questions as well. Not too lengthy, but I think all the questions is not going to be MCQ type and so on. Okay, so yeah, there can be some small derivation or some equation that you need to write and few lines of explanation for any questions and so on. I hope that answers your query. But what you can do is that you can email the NPTEL people and they will guide you. Okay, so in the last class, what we have seen is that wave function peaks around the center, and then the m was the angular momentum for the wave function, right? And as m increases, the peak also peak was also going to increase further and further away from the center, right? And what we have seen is that radius is also something related to this. LB R is proportional to root m, and then LB was the magnetic length scale. LB was simply root over h by EP, right? What this equation or what this particular expression signifies is that depending on the m of my wave function, it also determines or it also kind of tells us that where I am in the peak of my wave function is, right? So if there is m is very high, let's say you start from 1, let's say this is 1, then if you have m equal to 2, then the wave function is going to peak farther away from the center, and this is the center. Okay, then m equal to 3, and then there is farther away. Okay, so that's what the symmetric gauge tells us. So as if the theta and the r are not really independent, right? So okay, yeah, so this tells you is that, so by theta I mean we are in the 2D polar coordinate, right? So as if theta is associated with m angular momentum and r are not independent. So these are both theta and r are the coordinates of polar. I mean, in the polar coordinates, right? So you have a, let's say, x and y. In the xy plane, you can denote the position of a point by this is r, and then this is theta. Let's say. Okay. Okay. So what we have is that as if the theta and r are not independent. Now, to understand this picture better, I mean the quantization of plateaus and how the edge plays a role, we go to a geometry called Corbino geometry. Okay, so here imagine you have a something like this, and then Okay. And then so imagine that you have a magnetic field applied. So this is a kind of disk. So this part is filled, let's say. So if I, so this is a hollow disk actually. So this part is filled. Okay. And then you applied magnetic field along the z direction. So so the disk is along the disk is in the xy plane, and you apply magnetic field along the z direction. B is parallel to the z direction. Okay, so then any point, so if we have this coordinate system x, y, and then this is z cap, then any point in the disk you can represent by r theta, right? So you have some r, let's say r, and then with the x-axis, let's say, or yeah, you can do the x-axis also. So this is the theta. So if that is the case, then then we imagine that the current is applied along this direction. Okay, if so, the applied current is along the this direction, along the radial direction, or sorry, the theta direction. So I is parallel to the theta direction. So that means that if you measure the voltage between these 2 points, let's say, uh, use a different colors. So these 2 points, so this will give you the rho xy, right? Because Hall voltage means you are essentially measuring the voltage perpendicular to the applied current, right? And this is also perpendicular to the magnetic field. So this is consistent with the geometry, rectangular geometry that we consider, right? So in our sample was something like this. Yeah, you have source here and drain here. You are applying current here, and then you have a lead perpendicular to the current, and you are measuring. Sorry, you are measuring the voltage somewhere here, all voltage, right? And then magnetic field is also applied along the perpendicular direction. So your current and then magnetic field and then Hall voltage was all perpendicular. Okay. And this is I mean, the same thing is also we are trying to construct here using the Corvino geometry, where your current, sorry, the magnetic field is along the Z direction. The current you apply is along the theta direction, and the Hall voltage, so rho xy you measure, is along the uh, radial direction, right? So this is the radial direction. So geometry wise, it is consistent. It just turns out that for the symmetric gauge, the Corvino geometry is very useful to understand the quantum Hall physics. Okay, so we have this geometry. So imagine we have a continuous infinite system. Okay, so earlier, let's say, let me draw this. So you have okay. Okay, so imagine you have this. This is, let's say, M1, M2, M3, M4. Okay, and this is the center. So this will be my R direction. Okay, so M. Okay, okay. So so what I'm trying to draw is that the wave functions for different M's. Okay, So if you have seen my last lecture, what you have seen is that M, so and these are in the increasing order. So M1 is less than M2, and then M3 is greater than M2, and so on. Okay. So you have a wave function. Okay. So you fix the, let's say you fix the, you are at the n equal to 0 Landau levels. So this is n equal to 0 Landau levels. Essentially, you have Landau levels something like this, right? And then you have n equal to 1 Landau levels, let's say. Now, what we have seen that epsilon n for graphene also. So this was something like this: 2 mod n h bar vf square. So the energy was independent of m. M was another quantum number, whereas the wave function, so wave function was dependent on m, right? So our wave function was n and m dependent, which you can write as a dagger to the power n, b dagger to the power m by I think n factorial, m factorial. This acts on the ground state, okay, zero state. So this was the wave function. Uh, so this was the wave function which depends on m. M was the angular quantum number, and then n was the simple, I mean, the number operator basically, which we have seen in the harmonic oscillator case as well, the basic quantum mechanics. Okay, so what this tells you is that the energy only depends on the m, sorry, n, but it doesn't depend on the m. So for a series of, so what I have done here in this plot is that the Landau level energy is as a function of m, but since the Landau levels are independent of m for any m, I have drawn few m, but there are huge number of m because m determines the degeneration of these Landau levels. So for any m, you have a fixed energy level, right? As long as n is fixed. Again, for you go to higher n, you have a series of, I mean, series of m values along the x-axis. You have the same uh, energy, and so on. It goes on like n equal to 2 and so on. So here I have plotted, or at least trying to show the peaks of the wave function for m equal to 1, and this is the origin, let's say the center point. So this is where the wave function for any particular n. So okay, so let me fix n. So let's say this is n equal to 0. Okay, now for n equal to 0, you have some m, your wave function peaks around the energy, sorry, around the origin, and then you increase the m, right? The wave function peaks goes farther away from the origin, so radially it increases, and then you increase the m to m2 to m3, again it goes away from the origin, and this keep on happening, right? Now, in this picture, in this Corbino geometry, so this is a continuous geometry. It started from 0. We are not saying that this M1 is 0, okay? Because we are in a continuous geometry, somewhere m equal to 0 lies here, okay? Because if for m equal to 0, the wave function exactly peaks at the, uh, uh, I mean, origin. Now, so this is a continuous spectrum and continuous geometry. So let me write that. Now we want to create a discontinuous geometry, or creating an edge, right? By edge, I mean physical edge of the sample. So that's what we want to create. So what we have is that I just can copy this. Okay. Okay. So creating an edge essentially means, at least for this Corbino geometry. So this is what we are trying to understand. So in this picture, so how do I create edge is that you create, so let's say this one, and then you are creating an edge somewhere here, let's say. Okay, and there are many other I mean circles like this which I am not drawing here, but I'm just showing the two just to present the idea. Okay, so the creating an edge essentially means that this creates an creating an confining potential uh, which which confines the electrons. Within a certain boundary, let's say. And this is something we all know, right? Because in basic quantum mechanics, what you have seen is that you have a way, I mean, free particle, right? Free particle which have wave function which goes as e to the power I k dot r. You create a confined potential. So this sorry. This particular wave function. So this particular wave function means it is delocalized, so it is present everywhere, and then you create a confining potential, right? So 1D potential box, let's say, 1D potential box at, let's say, x equal to 0, and others at other some point other end x equal to L. And because once you create this confining potential outside this, the V is infinity, let's say, right? 1D potential, I mean infinite potential box, then your electrons or the particles is going to confine here, and their energies will be quantized, and your wave function will be sine n pi x by L and so on, right? So this is what we are, I mean, the something similar we are trying to do earlier. So this was the continuous geometry, and then we are trying to confine here, right? So trying to confine means so at around these edges at this r value and this r value. So these are my I mean continuous geometry we have, but then so these are essentially creating a disk like behavior. I mean Corbino disk. Okay. Okay. Now we want to see how this particular part corresponds to in a finite geometry. So just to show you. Okay. So we are having. So this is my energy levels, and then uh, so some energies, right? So this is, let's say, n equal to 0, and then this is, let's say, n equal to 1, and there are some I mean these are different m values. Okay, so this is along m. Now, what we are trying to create is that we are trying to restrict or confine the geometry. So as we confine the geometry, as you can see from this picture, that we have confined the geometry from here to here, let's say, right? So that means the M1 will go out, right? Outside this geometry. So this is my continuous region, and these are a hollow region basically. So these are also hollow region, and this is also hollow region, like a hollow disk. So what we have in terms of confining potential is the following. So we have, so this is, let's say, R direction. R again, so R direction is equivalent to R, M, right? And remember that R was root M L B, right? And then we're trying to confine it. So this was, let's say, M1. So this was M1. So this was M2, M3, M4, and this is M5, let's say. So you have constraint to M2 and M3. So let me increase a bit so that it looks. So I want to confine here, let's say. Okay. And I have another layer, which is M4. Sorry, M5. This will be M5. Okay. So we have three M2, M3, and M4. So what we have is that M2 will be within, so M2 and then M4. So we have something like this. The potential will looks like this. Okay. So this is confining potential as a function of R. So this is R corresponding to R in, R inward, or you can think of as a M1, right? Because up to this we are confining, and then R out. So in this adjacent picker, it is M4, more than M4, right? Okay, so this is the confining potential we have. So once you consider the finite geometry, your earlier the potential is again zero, right? Within this geometry, we have so we have potential zero, and then at the boundary there is some potential. So this is called edge potential. Okay. It's you can think of like 1D potential box, but this is not an essentially infinite. The potential is definitely not infinite. It has some value. Okay, and within this, you have a zero potential as expected, right? And so here in this case, so in this case where we have a continuous geometry, infinite geometry, the potential was exactly zero at everywhere. Okay. Once you create an edge finite sample, the potential is zero within the sample, and then there is a so these are physical edge of the sample. Okay, you can think of. So so this is, let's say, physical edge of Corbino geometry. Okay. Now, because there is some potential at the edge, now what really happens to the Landau levels or the energies at the edge, right? So the Landau levels with this M, so this M's M2, M3, and M4, let's say, right? So these have the same energy because it is well within the bulk, so it has the same energy. But then for this M1 and M5 and so on, so they experience an extra potential, right? VR is not equal to zero here for M1, let's say. So VR is not equal to zero. For M5 also VR is not equal to zero, right? So the wave function for M2, M3, and M4, they remain same, but then the electrons corresponds to the wave function of M1 and M5. They experience extra potential of VR, right? Once they experience extra potential energy of VR, so their Landau level energies also get increased. Okay, so if we try to plot, I'll have to plot in the same scale. So this is, let's say, M, and I have Landau level energies, let's say. So this will be at some higher energy, and this is M2, M3, M4, M5. M5 will also be at some higher energy, and then there are other M's which I have not drawn, right? So here also I have not drawn. Okay, so this was my n equal to 0 levels. So earlier this was my n equal to 0 levels, right? And so this is, let's say, M1, M2, M3, M4, M5, and so on. So up to this we have the same energy as earlier. So this is equal to n equal to 0 levels. And M5, again, they experiences a extra potential of VR, so they bends, right? So it doesn't look good, but let me try to redraw. Okay, and then there is another. So these are exactly flat, and then it starts increasing. Okay, so the picture is not really good, but yeah. So n equal to, so this was n equal to 0, and this was n equal to 1. So this one. Okay. So what happened, because there is a finite edge in the sample or in the Corbiner geometry, your states with uh, uh, so the electronic states with M2, M3, and M4, which is well within the bulk, right? Well within the bulk essentially means they are within this boundary, right? So this M2, M3, and M4. Okay, so let's show my miss. Yeah, so this is sorry. So this is M2, this is M3, and this is M4. So let me write M4 here. So this is M4, okay, and then there is a boundary, and this one is M5. It's disturbing. Okay, so M2, M3, and M4 are within the bulk, so they have the same energy as earlier, right? And then M1, and then below the angular momentum values M which are below M1. So let me write it clearly. So M2, or the electronic states, M4 have same energy as in bulk, because they are within the bulk, that is the reason. And then the states with M1, and more importantly, for all M less than M1, uh, and M, so let me write for all actually. So M less than equal to M1 and M greater than equal to M5 have higher energy due to the confining potential V of R at the edge. Okay. Okay, so this is what is represented here, that you have same energy, and then that means that Landau levels bend towards the edge, and these regions are actually the physical edge of the sample. Okay, now imagine you have a Fermi energy somewhere here. So somewhere here you have a Fermi energy. Okay, for chemical potential. What that means is that the electrons below this Fermi energy, below this energy, all are occupied, right? Okay, so let me also write, so the states, so these are the states, these are the states of different colors. states at the boundary of the geometry or sample. Okay, so okay, so once you have these higher energy Landau levels, now let's try to see. Uh, so, so now let's try to see what happens to the electrons or the states of this region. Let's say, okay, of this region and this region. So these are the two ends of the coordinate geometry. Or, this will represent also the two end of my physical sample, rectangular sample. Okay, so so essentially what we have is that del epsilon del m is kind of velocity here, and it represents the theta direction, right? And that is because del epsilon del r is essentially equivalent to rather it is equivalent to del epsilon del m. M and r I mean are related. So this del epsilon del m represents velocity in theta direction. This is just like the velocity in the Cartesian coordinates or the rectangular geometry for Vx. We have 1 by h bar del epsilon del kx, right? And then Vy is 1 by h bar del epsilon del ky. Similarly, we have a r theta dependence here. I mean, the geometry is such that so del epsilon and del m will be the. I mean, sorry. So sorry. So what I'm trying to say is yeah. So the velocity in the theta direction is essentially you will think that del epsilon del theta, but then theta direction is essentially represented by m, right? So we have a del epsilon del m as a velocity along the theta direction. And remember the theta direction was this. Uh, so if we go to the coordinate geometry, then this was my theta direction. So this was the velocity uh, uh, along the current direction actually. Okay. Okay. Now so that means now the important point is that del epsilon del m. Okay. So the del epsilon del m, the del epsilon del m is positive for uh, outer radius of Corbino geometry, and del epsilon del m is negative for radius of Corbino geometry. Why this is the case? This is just you can see that as you are increasing m here, right? So m5, m6, and m so on. The epsilon is also increasing. So del epsilon del m is positive here, and then as you are increasing, so the del epsilon del m is decreasing here, right? Because as you go here from m1 to let's say lower m, then the energy also increases. That means that your del epsilon del m is negative here, and then this is positive here. It's just the slope with the m, right? So this is a slope, so it is negative, and this is a acute slope, so this is positive. Okay. So what this necessarily means is that the eighth state in the Corvino geometry looks something like this. So you have a, uh, I mean, two edged in the Corvino geometry, right? So the because the velocity are positive and negative, let's say, so this was our M radius, right? So R outer, let's say, and this was, let's say, R inner, right? So along this you have a positive velocity, but then at the R in you have a opposite velocity. So that's what we have seen. So one is positive and one is negative, right? So the electrons at the two edges. So what I'm trying to say is that electrons at the two edge flows in opposite direction, right? Okay. Now, what electric field? Remember that in the Corvino geometry, we have applied that the current is along this direction. Current essentially means you have applied an electric field. Okay. So, what electric field does is that there is a force on the electric field which is minus E of E, right? So it applies force in opposite direction to the electrons, right? At least for the negatively charged particle. So there will be a disbalance between these two edges, right? So the velo initially, if you do not think about the electric field, that means you have a equal number of electrons going in this direction, equal number of electrons going are coming along this direction. So along both the edges of the sample, here these are the edges. So the equal number of let's say going along plus theta direction and equal number are coming along the minus theta direction. So you have no voltage, right? But then once we apply the electric field, the electrons more will try to come along this direction because the force is the negative direction to the electric field, right? So the more number of electrons will sort of come here, and then less number of electrons will be there. So that means that you have a you have a finite, I mean, difference between the number of electrons at this edge and at this edge, right? Remember that in the Corbino geometry, I said that this will be your Hall voltage, right? So the voltage here you will measure will be rho xy, will give you rho xy basically. And this voltage develops once you apply the electric field, right? Because the more number of electrons here will be there, and then less number of electrons will be there. So that sort of explains that why there will be Hall voltage uh, even in the gap. So let me re-emphasize this point. So all of these points, so all of these geometry where your Landau levels, I mean, some of the states are exactly staying, the bulk states are exactly staying at the same energy, right? Whereas at the edge of the sample, there are some states which acquire more energy because of the confining potential, and then the confining, I mean, the velocity of the states for outer radius, which is this M5 and so on, was positive, right? Because it had an acute angle, and then it has a negative at the other end of the sample. All of this is in the equilibrium. You have just applied magnetic field. There is a development of the Landau levels, and because of age, how the Landau levels looks like. So this is the Landau level. This is how the Landau levels looks like in the when you consider the physical age of the sample, right? But it still doesn't give rise to the transport. The transport only appears when you apply an external electric field or the current. This is equivalent. And this current creates the disbalance between the number of electrons flowing along one edge and between the other edge. Okay. And this disbalance between the two edges in terms of number of electrons appears as a Hall voltage. And remember that the my Fermi level is somewhere here. So the Fermi level is still in the bulk band gap, right? So these are this is the band gap between the two Landau levels. If you think between these two area, if you forget about the edge physics, so within this area you have this perfectly flat Landau levels, and then your Fermi energy lies somewhere here, right? So you have a gap in between. So your rho xx is 0, right? So there is no longitudinal resistivity. But then once you consider the age, so there are some states to conduct, right? So there are some states which goes along this direction, some state go along this direction, and once you apply the electric field, there is a the I mean, the disbalance between the number of states comes along this direction versus the goes along this direction. So this disbalance creates a finite Hall voltage, uh, whereas because you are in the bulk band gap, your Fermi energy lies in the bulk band gap, your rho xx is zero. And what explains this stable plateaus? So as long as you are your Fermi energy is in the bulk band gap, right? You have the plateau because essentially, I mean, essentially you are not increasing the more number of electrons, let's say. Okay. Yeah. So let me explain how do you get that quantized value of these I mean and the Hall resistance, then it will be more clear. So what really happens is that if I want to draw this again, so I'll this time I'll draw more number of M's so that the picture is more clear. Okay. So this is, let's say, one Landau label. So these are the cross signs are different M values. This is one Landau label, and then there is many others which I'm not drawing, of course. Okay. So this is, let's say, n equal to 0 Landau labels, or let me write here. So this is n equal to 0 Landau labels, and this is n equal to 1 Landau labels, and these are edge effect. So we have uh, epsilon n versus m. Okay. So what the electric field does is that electric field creates a disbalance between the, so because of the positive velocities, let's say it goes along this direction. Once you apply electric field, and this comes along this direction, so the electrons have a opposite velocity. So here v theta is, let's say, positive. Here v theta is negative, let's say. V theta is negative. Okay. Okay. Now once you apply external electric field, the picture slightly changes. Okay. So earlier, let's say, imagine you have something like this. Okay. And then as you apply the electric field, what really happens is that something like this happens. Oh, let me draw a bit more carefully. Okay. Okay. So this was at, let's say, electric field or current, uh, electric field or current equal to 0, and this is at a finite electric field. So this is at a I not equal to 0, or electric field not equal to 0. Okay. And remember that electric field is along the radial direction, right? So along the radial direction, you applied electric field. This creates the disbalance between the number of electrons in one edge over the other edge, and this appears as a Hall voltage. So if we try to calculate or sort of estimate, so this is what we are so yeah, so this is what we are estimating, okay, not precise value. So I want to calculate the current along the theta direction, right? Why theta direction? Because if we again go back to the Corvino geometry, so yeah, so if we go back to the Corvino geometry, so the current was along the theta direction, right? So that's what we are trying to estimate, and from there we will try to have a uh, idea of Hall voltage, what should be the Hall conductivity. So the current in the theta direction will be M in from M in to M out, right? So what is M in? So M in essentially means if I go back to that geometry, so you cut off from here, right? So you start from let's say M1 was not there, so start from M2. So this is your physical boundary, right? So let me write here actually. So this represents edged, okay, edged of sample or Corbino geometry, okay, where R in is the inner and R out is the outer radius. Okay, so the reason is you start. So this is, let's say, assume as in, right? So within the R in, let's say, and then this is our highest M that can be accommodated within the finite geometry. So this is, let's say, M out, and this is, let's say, M in. Okay. So what we have is that the current goes from, I mean, the number, the angular momentum number goes from M into M out, and it is we are integrating over dm. We are integrating over dm because that is how many number of states are there, right? And then v theta. So what we have is that dm by 2 pi, and v theta is just, you can actually, sorry, this is h bar del epsilon del m. Hmm. This will be I theta equal to E by H epsilon m out. Uh, so these are just estimates. So let me write as a just estimate. So this will be m out minus epsilon m in. Epsilon are the energies corresponding to m, and this, remember this is the corresponding to one Landau level, right? So we are kind of focusing here only. Okay, so this is, let's say, m in. So let me write down. It will be better. So this is, let's say, my m in, and this was, let's say, the physical. So somewhere the Fermi energy was lying here. M out. Okay. Okay, so now what will happen is that this is the energy difference between M out and M in. Now the energy difference will be equal to, so the energy difference equal to, sorry, disturbing, mu out minus mu in. So the chemical potential difference, which is equal to voltage applied, right? So this will be equivalent to EVH. or sorry, voltage generated actually. EVH. Okay. So this then we can write as I theta is of the order of E H, and then mu 1 minus, sorry, epsilon m out minus epsilon m in is essentially mu out, chemical potential difference between the two edges, and which is again appears as a Hall voltage, right? So E by H, EVH. So it is of the order of E square by H, VH. And from this relation, we can think that sigma xy. So this was our applied current, and this is the generated voltage. So sigma xy will be of the order of E square by H. Okay. And remember that we had a rho xy. So rho xy, where the plateaus were 1 by nu is, sorry, H by E square, right? So so this sort of give you estimate that rho xy when the Fermi energy is within the, I mean, bulk band gap. So Fermi energy is somewhere here. Fermi energy is essentially somewhere here. So within the gap of the two consecutive Landau level, where rho xy is, sorry, rho xx is 0. So then the rho xy will be just the inverse of sigma xy, right? So this means this is already, this factor is already here, and this was extra factor in the uh, experimental plots. And so as you consider more and more Landau levels, what will happen is that so this is, we considering the one Landau level. If you consider two Landau levels, you will get 2 e square by h, and then if you inverse that again, you will get 2 h by e square, right? So this sort of explains you the the appearance of Hall voltage and why these plateaus are stable. Okay, these plateaus are stable because of the edge, and of course there is a role of disorder also that is being played out. So so just to remind you that we started with the question, at least for the second part, we started with the questions that we what explains the plateaus in the rho xy, right? So that was our question. Now, how do you explain this? So we started with again the continuous picture. You have a bulk a periodic system. There is no concept of age and so on. So you have a Landau levels at n equal to 0, n equal to 1, and so on. And this Landau levels were sort of represented in the Corvino disk geometry, where I have a different m values for a single Landau level. Okay, so this is for a single Landau level, n equal to 0, and we had a different many wave function for this particular energy level represented by these circles m1, m2, m3, and so on. Now we tried to construct the physically what is happening at the in the real sample, because the real samples are essentially finite. It is not an infinite periodic system, right? So so in the Corvino geometry, what we have done is that we have I mean tried to we constructed a finite geometry by having, by saying that this is my R inner and this is my R outer. So this is my, these are my physical edge of the sample, right? So these are vacuum, and then this beyond this R out also there is vacuum. So because of this, essentially there is a whenever there is an, I mean, finite system, there will be some edge potential, right? And because of this edge potential, your perfectly flat Landau level, which was true for only, I mean, infinite system or bulk system, your Landau level energies are going to bend at the edges. So these are, so these bending are happening at the physical edge of the sample. Okay, within the bulk, they are perfectly flat as it was earlier case, and importantly the states at the edge. So these are, this is one edge, this is another end, end of the sample, and in the two end the sample, I mean the states, electronic states are having positive velocity and the negative velocity. So this we represented by this particular figure. You have a Corvino geometry, finite geometry, and then at the physical edge, the electronic states are moving with exactly opposite velocity. So these are also called chiral state. Okay, chiral state, because one is moving along this direction, another one is moving along this direction. Now, once we apply external electric field as well, which is already there in our I mean experimental setup, because the electrons feels this kind of force, right? The electric force, the electrons try to I mean, move in the opposite direction to the applied electric field. So the more electrons will move along this direction, right? Than this direction, and because there is more electron here than this part, once you measure the voltage, which is the perpendicular direction to the applied electric field, as well as the applied magnetic field, which is along the z direction, so this voltage appears in this as a Hall voltage. Okay. And why this is quantized? Because as long as your Fermi energy is within the bulk band gap, so considering that one Landau level is occupied, you are having the conductivity of the order of E square H. But if there are two Landau levels are occupied, then you do the same calculation again. So this was for one Landau level, M in and M out, right? Remember that energy was independent of M; it was only dependent on N. So you can construct the similar Corbinian geometry for n equal to 1 when your Fermi energy lies somewhere here. It also covers the n equal to 1. Now you do the same calculation for n equal to 0. You already get this kind of this conductivity. For n equal to 1, exactly same calculation follows out. And then this will also give rise to another E square by H of current. Okay, and this will give rise to sigma xy to be E square by H plus another E square by H coming from n equal to 1, and as a result you will get sigma xy, here it will be 1 by 2 H by E square. For n equal to 0 it was 1 by it will not be 1 by 0 actually. So these are so these new starts from 1, 2 and so on, where the new actually nu equal to 1 for n equal to 0, and nu equal to 2 for n equal to 1, because yeah, so this is how the way we start from n equal to 0 and so on. But the crux of the story is that the quantization values, what will be the quantized value is determined by the fact that how many Landau levels are occupied, or how many Landau levels are within below the Fermi energy, right? So if you have a two Landau levels below the Fermi energy, you have a 2 E square by H of Hall conductivity, quantized Hall conductivity, and so on. Okay, and what the explains plateau, because as you so somewhere here, let's say you have the Fermi level, right? Somewhere here you have Fermi level. So you are essentially having one Landau level within the Fermi level. If you change the Fermi level to here, again there is only one Landau level. If you have here, again there is one Landau level. As long as you are not crossing the second Landau level, your the conductivity is going to be the same. That's what at least our Corvino geometry from the Corvino geometry explanation says. Okay, so this explains that as you increase the magnetic field, that's what the experimentalists do, or they also do the increase in the carrier density. But if we increase the magnetic field, I mean, so as long as so somewhere here, let's say your Fermi energy is fixed, right? So you are increasing the magnetic field value, and then the whole Landau level energy also gets increased, right? So let me draw here, maybe. Okay, let me draw another figure. It will be very uh, so so you have two Landau levels. Let's say I'll only talk about two, but this is essentially general for any number of Landau levels. Okay, so if we have, let's say, Fermi energy here, right? Just crossing the n equal to 0 Landau level. So Fermi energy. Now, as you increase the magnetic field, okay, so what will happen? Okay, so let me start with higher Fermi energy, then it will be easy to explain. So this is my Fermi energy. Okay. Now I'll try to give you a snapshot of what is happening in the experiment as you increase the magnetic field. Okay. So I'll redraw this for 2, 3 times. So it was small, this one actually. So let me redraw actually. And then there is another I want to draw. Okay. So now consider what is really happening when the Fermi energy is, I mean, sort of. So initially, let's say we have Fermi energy here. So these are epsilon n. These are, let's say, r. Now, what's really happening is that once you increase the magnetic field, so let's say this was at some b equal to b1, b equal to b2, where b on is less than b2 and then b2 is less than b3. Okay, and this is b3. So what is really happening when you change the magnetic field is that my Fermi energy, let's say, stays at the same point. So at the same energy, right? So epsilon f, and then again, if I draw this at the same level, epsilon f. So what is really happening when you increase the magnetic field? So these Landau levels, okay. So these Landau levels will increase, right? Increase in their energy. So what will happen is that the so earlier this was something like this. So the earlier, let's say this was here, right? And then the upper level will also increase. So earlier this was here, and then as you increase further, so let me draw at the extreme. So somewhere here, let's say, and then it goes further away. Okay. Okay. So as you increase the magnetic field, so you have Fermi energy is fixed because carrier density is fixed. So you had somewhere here, you are getting the conductivity as E square by H. So let me write here n equal to 1, just not to be confused, n equal to 0, and this is n equal to 1. Okay. So initially you have Fermi energy here, B equal to some B1 value, right? So you have again, so within this level, you have quantized Hall conductivity to be E square by H. You increase the magnetic field by some amount, so the energy of these levels also increase. So the n equal to 0 Landau level gets closer to the Fermi level, whereas n equal to 1 level goes further from the Fermi level, and more. So then you increase the magnetic field further. So again, it almost comes very close to the Fermi level, whereas the n equal to 1 level goes farther from the Fermi level. But as long as this up to this limit, as long as your Fermi, I mean, so the n equal to 0 level lies within the Fermi level, right? This means you will always have the conductivity of E square by H, hence the resistivity of H by E square. This is one. Now, the moment it crosses, so suppose you have so you increase the magnetic field B4 to be greater than B3 such that your Fermi level, sorry, the Landau level somewhere here, right? So that means that it will not be E square by H, something else, depending on how many, I mean, in which Landau level it goes. So for this range of magnetic field, your Fermi level lies within the bulk band gap, right? So the bulk is gapped, but then because the edge states are conducting, so these are the edge states which is conducting. Remember the del epsilon del m for this particular states are zero within the bulk. These are these. So let me rewrite. I forgot to write before that. So zero for bulk state, right? So bulks are not conducting because the velocity itself is zero. So they are not conducting. So what is conducting is the states at these edges, right? And as long as you have a one, let's sorry. Uh, Okay. So as long as you have this one Landau level within this Fermi energy, you have E square by H of conductivity. Okay. And then if you have two Fermi level, again two E square by H. The moment your Fermi level lies somewhere here, exactly, sorry, the Landau level exactly lies on top of the Fermi level. That means there are some state which we talked about, delocalized states, which can the electricity can carry within the bulk also, right? So the moment you have Landau level something like this, exactly on top of the Fermi level, your bulk states are conducting because there are some electrons delocalized, which can conduct electricity freely. And that give rise to rho xx peak at some particular value of the magnetic field. Okay. But as long as you are within the bulk band gap, you have a plateau of rho xy, your bulk states are not conducting, which you can also think from this particular perspective that V theta is totally zero. So if V theta is zero, velocity is zero, the electrons will not conduct within the bulk. If they do not conduct within the bulk, you will not have any resistivity or conductivity along the longitudinal direction. But whereas the Hall direction, transverse direction, the velocity, I mean the electrons always conducts because of these edge states which give rise to finite Hall resistivity or Hall conductivity. Okay. So this was sort of the story uh, of the quantum Hall effect. So there are four things that is needed to understand the quantum Hall effect. So I'll just say this and finish this today's talk or and today's lecture. Uh, so you need 2D electron gas. It can be free electron gas or it can be graphene also included. Plus you need magnetic field. Plus you need disorder because disorder is what stabilizes these plateaus. Okay. And then you need uh, edge physics. So these are the four ingredients that is needed to explain completely the quantum Hall data. There are many other nuances and criticalities that I have not explained, but broadly you understand the quantum Hall physics from this perspective, at least the integer quantum Hall part. You have to add electronic interaction, and then there are many other parts in the picture to explain the fractional quantum Hall. Okay. Okay, so with this, I think we'll end here. If you had any question, then please ask me in the next lecture because nobody is there. Okay, okay. So I hope this will be helpful.